discuss about the activation functions. We all know that the brain receives the stimulus from the outside world, does the processing on the input, and then generates the output. As the task gets complicated, multiple neurons from a complex network passes information among themselves. So that is how the artificial neural network also work. So this is basically a neural network. You can see several inputs here and some processing happens here and we will get an output. If we look into this figure, we can see some inputs x1, x2, x3, xm, and there are weights w1, w2, w3 up to wm, and here the weights and inputs get multiplied and get added up, and the bias also gets added up. Then it is passed to activation function, and then finally we are getting the output. So here we can see some activation function. So in this video, we are going to understand what is activation function, and we are going to get a thorough knowledge, complete knowledge on activation function. So what are activation functions? Activation functions are mathematical equations that determine the output of a neural network. It takes the sum of weighted inputs as an argument and returns the output of the neuron. So if you look into this, we all know that x is equal to weight into input plus bias. So when you apply activation function, what happens to this equation? This is what we are going to discuss now, right? So generally, we write weight into input plus bias, right? This is what we say, right? So here we apply some activation function on that. Then it is applied on this particular function, right? And we get the activation function output. So what is happening here? It takes the sum of the weighted inputs as an argument and returns the output of the neuron. Activation functions converts a linear function into a non-linear function and allows non-linear decision boundaries. It can decide whether a neuron is switched on, which means it acts as a gate by applying a non-linear function on the input. There are many types of activation functions such as binary step function, tanh, sigmoid, SoftMax, etc. So this is the most important question in the interview. Why do we need activation functions? Just take some time and think about it. Why do we need activation functions? In the absence of activation functions, what happens? Imagine a neural network without the activation function. In that case, every neuron will be performing just the linear transformation, right? So what will happen here? We get w1 x1 plus w2 x2 up to wn xn plus bias. So basically, it does only the linear transformation on the inputs using the weights and the biases. It makes the neural network simpler. So this will make it less powerful so that we will not be able to learn the complex patterns from the data. So if there is any question on this, you have to answer that a neural network without an activation function is essentially just a linear regression model. So we use a non-linear transformation to the inputs of the neuron, and this non-linearity in the network is introduced by the activation function. So basically, activation functions are used to introduce non-linearity, right? So here are some types of activation functions given. Binary step function, linear activation function, non-linear activation functions. You can see sigmoid function, SoftMax function, tanh, Relu, which is nothing but rectified linear unit, leaky Relu, swish. So binary step function is a threshold-based classifier. Linear activation function is better than a step function because it allows multiple outputs, not just yes or no. Sigmoid or logistic, here the output values bound between 0 and 1. Tanh or hyperbolic tangent ranges between -1 and +1. Relu is widely used but converges quickly. Leaky Relu is better than Relu and solves dying Relu problem. SoftMax can be used only in the last layer. So let us dive deep into the types of activation function. The first one, let's discuss about binary step function. Let me tell you in simple words, if the input to the activation function is greater than a threshold, then the neuron is activated, else it is deactivated. That is, its output is not considered for the next hidden layer. So how can I understand this? So let me write that f of x is equal to 1 if x is greater than 0 and this is equal to 0 if x is less than 0. Hope it is clear to you, right? So whenever it is less than 0, so that f of x becomes equal to 0, and when x is greater than 0, then f of x will be equal to 1, right? Okay. So this can be used as an activation function while creating a binary classifier. So as you can imagine, this function will not be useful when there are multiple classes in the target variable. Right? That is the major limitation of binary step function. Another point is that if you find out gradient for this, the gradient of the step function will be 0, right? So if you find f dash of x, that is going to be 0, right? Okay. So whenever you calculate the derivative of f of x with respect to x, it comes out to be 0. So now we realized the problem with the step function, that the gradient of the function becomes 0, right? So now let us study about the linear function. Here, instead of binary function, we use a linear function sometimes. This can be represented as f of x is equal to ax. This is very simple. Say for example, I can say that f of x is equal to 2x. Right? F of x is equal to 2x. So in case if x is equal to 2, then what will be f of x? F of x is going to be 4, right? Fine. So if x is equal to -4, then f of x will be equal to -8. Hope it is clear to you, right? Okay. So in case if I find the derivative for this, a gradient for this, what I will get? F dash of x is equal to 2. So here the gradient is not becoming 0, but instead of that, if I find a gradient for this, I'll be getting answer as A, right? It is a constant which does not depend upon the input value x at all. So this implies that the weights and biases will be updated during the backpropagation process. So here the neural network will not really improve the error because the gradient is the same for every iteration. So the network will not be able to train well and capture the complex patterns from the data. So linear function is ideal for simple tasks where interpretability is highly desired. The next activation function is sigmoid function. It is S-shaped curve and it is of the form f of x equal to 1 by 1 plus e power minus x. The value ranges from 0 and 1. Interpretation as a saturating firing rate of a neuron, right? So there are some drawbacks also. Output is zero-centered, it has vanishing gradient problem, and the convergence is really slow, right? Okay. The point to be noted here is, unlike binary step and linear function, sigmoid is a non-linear function. This means when I have multiple neurons having sigmoid function as their activation function, The output is non-linear as well. The sigmoid function is not symmetric around 0, so output of all neurons will be of the same sign. The next activation function is tanh. This is also similar to sigmoid function, but only difference is that it is symmetric around the origin and it ranges from -1 to +1, and this is preferred over sigmoid region, right? So this is of the form tan h of x is equal to 2 divided by 1 plus e power minus 2x, right? So otherwise, let me write this way. This would be easy for you. I can write that tan h of x is equal to 2 sigmoid, 2 sigmoid of 2x minus 1. Very simple, right? We know what is sigmoid x, right? So 2 sigmoid 2x minus 1, which is nothing but 2 divided by 1 plus e power minus 2x minus 1, right? Okay. So here, as I told you, the output ranges from -1 to +1, right? So apart from that, all other properties of tan h function are the same as that of the sigmoid function. And similar to sigmoid, the tan h function is continuous and differentiable at all points. And if you find out the gradient also, it will be steeper as compared to the sigmoid function. And tan h is preferred over the sigmoid function because it is zero-centered and the gradients are not restricted to move in a certain direction. The Relu function is another nonlinear activation function, and this is being very popular in the deep learning domain. Relu means rectified linear unit. The main advantage of Relu is that it is simple, much better convergence than tanh and sigmoid function. It is very efficient in computation, and the main advantage is that it does not activate all the neurons at the same time. This means that the neurons will only be activated if the output of the linear transformation is less than 0. So now if you look into this, maximum of 0, z, that is what I have written, right? Say for example, I am writing a Relu function for 7, then the output is going to be 7. If I write Relu function -4, the output will be equal to 0. It will be taking the maximum value. In case if you give any negative value, the output is going to be 0, right? So that is what you can see over here, right? So -10, -5 till 0. Whenever there are negative values, it corresponds to 0, right? Now the problem with Relu is that some gradients can be fragile during training, can die. It results in weight update and possibly never activating again. So to improve that problem, leaky Relu is being introduced. It is an improved version of Relu function. So instead of defining the Relu function as 0 for negative value of x, we define it as an extremely small linear component of x. So here you can see that f of x is equal to 0.01 x when x is less than 0, which is equal to x when x is greater than 0. In Relu, we were equating, when it was less than 0, we were writing it to 0. But here at least we have small linear component of x. So by making this small modification, the gradient of the graph, left side of the graph, comes out to be a non-zero value, right? So that is what our requirement. So we would no longer encounter dead neurons in that region. Since leaky Relu is a variant of Relu, for example, say like leaky underscore Relu underscore function of -4, if I give, I'll be getting answer as -0.04 instead of getting 0 like in Relu function. Hope it is clear to you, right? So the next one is parametrized Relu. So this is another variant of Relu. This also aims to solve the problem of gradient becoming 0 for the left half of the axis. So as the name suggests, it introduces a new parameter as a slope of the negative part of the function. So let us understand like what is the difference over here. f of x is equal to x when x is greater than 0, like the previous cases, but it is equal to ax when x is less than 0. So when the value of a is fixed to 0.01, the function acts as a leaky Relu function. In parameterized Relu function, a is also a trainable parameter, and the network learns the value of a for faster and more optimum convergence. So the derivative of the function would be same as the leaky Relu function, except the value 0.01 will be replaced with the value of a. Exponential linear unit, ELU. So convergence costs to 0 faster and produce more accurate result. Nearly zero main outputs. It is very similar to Relu except when inputs are negative, and ELU uses a log curve for defining the negative values. So f of x is equal to x when x is greater than 0, like all the cases, but it is equal to a into e power x minus 1 when x is less than 0, right? In case if you give ELU underscore function 0.1, it will be finding this value, right? It will be, so when I give 0.1, right? So what it does is just it applies into this function and it returns me the output, right? Hope it is clear to you. When x is less than 0, it returns me the output as a into e power x minus 1. If it is greater than 0, it returns the same value of x. Swish is a lesser known activation function which was discovered by researchers at Google, and this is efficient as Relu and shows better performance than Relu on deeper models. The value ranges from negative infinity to infinity. So f of x is equal to x into sigmoid of x, which is nothing but x divided by 1 minus e power minus x. SoftMax function is described as a combination of multiple sigmoids, and the sigmoid returns values between 0 and 1, which can be treated as probabilities of a data point belonging to a particular class. So sigmoid was widely used for binary classification problems. But suppose we have to solve multiple classification problems, right? Multiple class problem. How can we solve that? Multi-class classification problems can be solved only with the help of SoftMax. Here the function returns the probability for a data point belonging to each individual class. So you can see the expression over here. While building a network for a multi-class problem, the output layer would have as many as neurons as the number of classes in the target. Say for example, 2, 1 and 0.1. Now when you apply softmax function, what happens here? E power 2 divided by e power 2 plus e power 1 plus e power 0.1, so that the output is equal to 0.7. Similarly, if you substitute on this 0.2 and 0.1, if you substitute on this 1 and 0.1, you'll be getting the probabilities as 0.2 and 0.1, right? So these will be the probabilities in this case. So here the formulae for activation functions are given. For sigmoid, 1 by 1 plus e power minus x, tan h of x, I think you are aware of it, and Relu, Swish, leaky Relu, max out, and ELU. So how do you choose the right activation function? So we have studied about several activation functions. First of all, we should know which activation function has to be used and where it has to be used, right? So depending upon the properties of the problem, we might be able to make a better choice for easy and quicker convergence of the network. So sigmoid functions and their combinations generally work better in the case of classifiers. Sigmoids and tanh functions are sometimes avoided due to the vanishing gradient problem. And Relu function is widely used activation function, and it is being used in most of the cases these days. But if you encounter a case of dead neurons in our network, then the leaky Relu will be the ideal choice. Always keep in mind that Relu function should only be used in the hidden layers. As a rule of thumb, you can begin with using Relu function and then move to other activation functions in case Relu does not provide with optimum results. Hope you have a clear understanding on the activation functions.